Hi everyone, in this video we're going to go through section 6.6, applications to linear models, and we're going to start out by covering least squares lines. What we do here is we bridge the connection between the linear algebra that was developed in the last section and apply it to the different context of linear models, and this is the true connection to statistics of least squares regression lines. Okay, so that's what we're gonna build here, and we're gonna take notation from the previous section, the ax equals b equations that we were solving with the a transpose a and a transpose b because there was no solution. Right, all of that notation from the last section. We're gonna write it a little bit differently in this section. It's gonna be capital X is the matrix, and then we're going to use a beta equals y. So just different notation because we're looking at a specific application. All right, and we're going to give each of these guys names. X is called the design matrix. And then beta is called the parameter vector. And y is the not equals dash, y is the observation vector. Okay, so start out just with that notation. That's our first piece here. All right, so what is a least squares line? It looks like this. All right, a least squares line is y equals b naught plus b1x. Y equals mx plus b, y equals b naught plus b1x. We're writing the equation of a line, a best fit line, a least squares line. Okay, and so what we'll say is we're going to say given a set of points x1, y1 through xn, yn, xn comma yn, we want to determine those two betas, b naught and b1, that make the line as close to the points as possible. The line as close to the points as possible. That is our goal. Okay, so what do we actually mean by that? Well, let's draw a picture. Pictures are sometimes helpful. So here are my two axes, and let's say we have some points here in space. I'll put just maybe 5 of them there. And then our goal is to write this best fit line, this least squares regression line, y equals b naught plus b1x, to get the points as close as possible. So what does that mean? That means that this distance and that distance and that distance and that distance and that distance are as small as they can possibly be. Okay, that's the goal. And so in my picture, that right there is a data point. Right, that is some xj comma yj. That's my data point. And if I want like a point on the line right there, point on a line, right? How do I get a point on a line? Well, I would substitute the xj, underline it, I would substitute the xj into my equation there, okay, and produce some value. All right, and let me write that down. So yj is the observed value of y. Y sub j is the observed value of y. If I take and substitute xj into that equation, b naught plus b1 times xj, that is called my predicted y. And their difference, if I subtract observed and predicted, is called the residual. Again, if you've taken some stats in the past, you may have heard a lot of these terms. Now in this section, again, we get the connection to linear algebra and how a matrix produces this least squares line. Now the fancy definition of a least squares line, the least squares line is the line that minimizes the sums of the squares, that looks terrible, of the residuals. That is what the least squares line does. And it's called the regression line of y on x. That's what it's called. And the reason that it's the squares of the residuals, sometimes the data point is above the line, sometimes the data point is below the line, so the residuals are positive or negative. So we square them to, like in actually looking at the residuals and the sums and all that, we square them in order to be able to like add them all together. That makes them all positive. Okay, and let's see, what else did I want to write here? Oh yeah, that's right. B0 and B1, they're called the regression coefficients. So lots of terms I'm throwing at you here. Regression coefficients. Oops, too many F's. Now let's think about a really easy scenario here, a nice scenario. What if all the points were on the line? If the points were on the line. So to go back up and look at my graph here, if all of those points weren't above and below the line, but they were all 5 right on that red line, that would be like some awesome ideal scenario. But what would happen? Well, my predicted y would equal the observed y. So my equation b0 plus b1 x1 would equal y1. My equation b0 plus b1 x2 would equal y2. You get the idea here? My equation b0 plus b1 xn would equal yn if all the points were on the line. The observed is equal to the predicted. So I can take that system of equations and write it as a matrix equation, right? All of my coefficients on the first term are all 1. 1. Okay, so what do I mean by that? Let me highlight here. All the coefficients of b0 are 1, right? So the first column of my matrix here is 1. All the coefficients of b1, right? Those are my unknowns. All the coefficients of b1 are the x's, x1, x2, xn, right? That's over here, these coefficients, saying they're on the wrong side, but those are the coefficients of the b vector. My first highlighting should have probably been in front, but that's okay. And then, so that's my first matrix in my matrix equation. And then, let's see, the second one is those variables, the unknowns, b0 and b1, and that is equal to y1, y2, yn, right? So we take that system of equations and we can kind of rip it apart and write it as a matrix equation. If all the points are on the line, this would have a nice, convenient, easy solution, but in practicality, it's not going to. If the data points don't lie on the line, do not lie on the line, well, we have a procedure to handle that, don't we? Right? This has no solution. So what happens? It becomes, a least squares problem. Right? How do we solve a least squares problem? Well, if it's capital X, B is equal to Y, right? We're going to take X transpose times X, and B equals X transpose times Y. That is how we're going to come up with the best solution. That's going to produce the B0 and the B1 that get us as close as possible to all of those Y coordinates. All right, let's take a look at this first example. We got to come up with an equation y equals mx plus b, not really, y equals b naught plus b1x for this set of points. And the steps that we do is that we take are we're going to write down our design matrix x, and the first column of the design matrix is 1. 4 ones because I have 4 data points, and they're all ones because that's what the coefficient of b naught is, right? And then the second column, I'm going to go through my data points and write down their x coordinates, 2, 5, 7, and 8. Why is that? That's the coefficient, the other factor, being multiplied by b1, and then close that bracket, times, or actually, let me just write that way. That's my x. Then the b vector, the parameter vector, is b naught, b1. And finally, the observation vector, y, is equal to all of the y coordinates, 1, 2, 3, 3. Okay, so that's how we set this up, and our goal is to solve xb equals y with its least squares solution. Minimize the residuals. So I need to take x transpose times x. This is now we're going back to what we did in the previous section. X transpose times x, I'm going to jump right to the product there. 4, 22, 22, and 142. Then I take x transpose times y, 9, 57. So kind of some ugly numbers here. And we solve the system for 22, 22, 142 times b naught b1 equals 957. That will have a solution, and the solution, if you put it into reduced row echelon form in your calculator, is that b naught b1 is equal to, what is it, 2/7 and then 5/14. 2 over 7, 5 over 14. So that gives us the equation of our least squares regression line, y equals 2/7 plus 5 over 14x. Pretty cool stuff. All right, that is the equation that gets us as close as possible to those 4 points. Just for the heck of it, I wanted to try out another example with 3 points that did lie on the same line and see what happens. So those 3 points lie on the line y equals x, like we know that. So here, hopefully we know that. Here I've written down my design matrix. Here's my parameter vector. Here's my observation vector. Here is x transpose x, gives me this matrix. Here is x transpose y, gives me this vector. And then I take those two over here and set up my augmented matrix. And I did this so I didn't want to bore you with these details because it works. But it works out, and I just want to point it out because it's kind of cool. And in going through the row reduction, we get that matrix at the end, and that is my final column. So b naught is 0, and b1 is 1. So y equals 0 plus 1x, or y equals x. Whoops. Hey, it does produce the line y equals x even when all 3 points fall on the same line, and even when it's something that I could really simply do without any linear algebra. I can use linear algebra to something that my kid is learning in 8th grade or 7th grade math. And it works out, which it's kind of cool. Okay, now we come to the general linear model, which is a way to deal with non-straight lines. Right, in statistics, we have lots of different models. And so how do we use linear algebra to handle those types of models? We still use capital X, B equals Y. We still use that same equation, but the form of X of my design matrix changes from one problem to the next. Okay, it is a true design matrix. You design it to fit the model that you are creating. And what we're going to do is we're going to use a residual vector, and we're going to call it epsilon. We're going to use a residual vector epsilon, and we're going to write this as epsilon is equal to y, minus x times b, and then write y equals x b plus epsilon. That is our general linear model. Epsilon represents the residual that we want to make as small as possible. Once x and y are determined, x and y are determined, we want to minimize epsilon. We want to minimize epsilon. Cool. That's the goal. For this next example, you can choose to pause the video so you can read the setup. I'm not going to read through all of that for you, so go ahead and pause if you want to. But then I'm going to focus here on the equation that I'm trying to create, right? This is a parabola, and I want to design a design matrix that's going to fit that parabola. But first, let's write down a few equations like we did in the previous example, right? And that would be points on that line, okay? And so y1 is equal to b0 plus b1 times x plus x1, excuse me, plus b2 times x1 squared plus my epsilon residual. y2 is b0 plus b1 x2. I might mess up the subscripts here, so I got to be super careful. Plus b2 x2 squared plus epsilon 2. That's the residual at that point. Epsilon 1 is the residual at the first point. Okay, so that would continue on for every point in my model to the last one. Yn is b0 plus b1 xn plus b2 xn squared plus epsilon n. Okay, so that's what the equations would look like as I'm substituting the x's in to get my predicted y's, right? And I want to get as close as I possibly can to the observed y's. Well, let's now convert this to a matrix equation. My y's are on the left, so I'll put that the observation vector on the left. This is y1, y2, dot, 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 yn. That's my observation vector. The design matrix I'll come back to in just a moment, but that gets multiplied by my parameter vector, b0, b1, and b2, and then plus my residual vector, epsilon 1, epsilon 2, dot, 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 epsilon n. Okay, so let's set up our design matrix. Oh, right, I wanted to write this is y equals capital X beta times beta plus epsilon. Design matrix. Time for that. What is here? What's the coefficient of all those b naughts? Well, it's 1. 1, whoops. 1, 1, dot, 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 1. All right, start off to a good start. What is the coefficient of all the b1s? Well, it's my x's. X, let's stick with blue. x1, x2, dot, 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 xn. And then finally, what's the coefficient of all of my of all my b2s? Well, it's the x's squared. So x1 squared, x2 squared, xn squared. So my design matrix, it's pretty much the same as the previous example, but we add on that quadratic term, which adds a new column. It adds a new entry in my parameter vector, and it adds a new column in my design matrix. You design the matrix to fit the problem, right? Maybe your parabola doesn't have a constant term, right? Then you wouldn't have that first column. Maybe yours is a cubic, it has a cubic term and a squared term, but nothing else, right? Then you would design the matrix to fit that problem. If yours had a sine wave in it, you would have some trig column. Okay, so it depends on the problem what the design matrix looks like. But that's as much as we had to do for this one. We weren't given any actual data points to solve, but that is our linear model that would produce a least squares fit of the data in this problem. Example 3, we'll just look at this one and kind of write down just the design matrix. Again, pause the video if you want to read through all this. But we're given our equation here, y equals b naught plus b1x plus b2x squared plus b3x cubed. So my design matrix is 1, 1, dot, 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 1, x1, x2, dot, 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 xn, x1 squared, x2 squared, xn squared, and then, oh, we got an x3, or we got a b3, so x1 cubed, x2 cubed, xn cubed. Okay, that is what our design matrix would look like. Our b vector would have 4 entries. Our y vector would be the same as it was in the previous problem, but this is the design matrix that changes as you encounter different scenarios. And that is where we will stop for this section, a pretty cool tie-in with statistics. Thank you very much for listening. Get started on the homework. Let me know if you have questions on the video or questions on the homework, and have a wonderful day.